Now we're good. Okay. Sorry.
So yeah, this is a picture that I took back in 2016, the night of election, when I was staying with my friends in New Jersey. Looking at New York, was deep in thoughts that in few hours, a decision will be made by a large number of people that will affect not only my life, but also a large number of people all across the nation. Me and my friends were almost sure that our expectation will come true in a few hours, but contrary to what we were thinking, something apparently different was about to happen. Something that not only was surprising and shocking for us, but also for a large number of people all across the nation. So in many other cases in collective decision making, we have setups where we have people embedded within social network, where some of the people supporting one party versus another party. But one feature of this network, of this ecosystem, is that in many settings, people are kind of receiving information or interacting with other like-minded people. So a key question in understanding this kind of ecosystem is that how do people make collective decisions in the presence of information biases and adversarial bots? That is, the structure of the network in which we are embedded plays a key role in a way that information spreads from one individual to another. And in these ecosystems, there might be bad actors or propaganda bots, or also maybe humans who are promoting some specific content. So it's important for us to model the way individual make decisions in this setup, and then helps us to come up with interventions in these ecosystems. So in order to answer these questions, we create a voting coordination game to better understand human behavior in this collective decision making on networks. So the set of our models as follows. Each individual is assigned to a political party or a color, that is the preferred party. And then the players have to vote on the outcome of an election. They can change their votes during the course of game at any moment of time, and they can also receive information real time from the other people in their social network. That is, I can see what the intention of vote of my friends within my social network, which is a portion of the whole population. And then, when the game concludes, there could be a winner that we define as the team or the party that has supermajority votes. In our case, like 60 or 70% of the whole population. So if the party who wins the game will get higher payoff, in our case $2. The party who loses the election will get 0.5, which is the lower payoff. And if the deadlock happens, none of the party get to the threshold, there is a deadlock. So none of them will get nothing. So the dilemma here is for each individual either vote for their own party, which is a higher payoff, but there would be like chances for getting a deadlock, which is nothing. So maybe they will also consider to vote for the opposing party, which is like 50 cents in this case, which is better than nothing, but not as great as $2. So in order to understand the dynamics in this setup, sure.
Why is the payoff of losing higher than the payoff of a deadlock?
So think about the case that you want to it's better for you to come kind of consensus with your opposing party than not coming to any consensus. So we designed an experiment to study how people behave in this setup. So, we designed a voting coordination game on a platform called Breadboard, which is a online platform for simultaneous interactions between players, and the vote by the team at Yale, Nicholas Christakis' team at Yale, to, let me see if, okay, it's a little bit, yeah, to recruit subjects from Amazon Mechanical Turk and then have them play this game on the network. I know there are like other platforms for designing such experiments to have groups of people interact at the same time, but the main reason that we went for a breadboard was that it was used in similar setting before, and in our case was more kind of like a economic game set up on network, so it was super optimized for that purpose. Here's the subjects that we recruited all across the world, mainly in the US and India. We recruited people in batches of 18 to 24 people and embed them within social networks. So the number of players depends on the experimental conditions that we were studying. And then once players joined the game, they were assigned to teams, and they were told if their team wins, they will get $2. If their team loses, they get something 20 cents to $1, depending on the experimental conditions. And then if the deadlock happens, none of them get nothing. And then we had supermajority threshold 60 to 70%, which was different for different waves of the experiments. Here is the timeline of our study. So first phase, I don't know, for some reason, the steps of the animation don't fit for like Keynote for whatever reason anyway. So at the first step, we had players join the game. They went through a tutorial, which were about how they're gonna act throughout the game. They went through a quiz, which was more kind of like a comprehension test. So whether they understood the payoff structure of the game. And then who couldn't make the quiz were allowed to participate in the actual game. And they will all enter a waiting room where they waited for the game starts, and then we have enough players to put on the network structure. And the game runs for 240 seconds with real-time local polling information. And all the clicks were recorded from all the players. That is, every decision that a player makes is recorded, and also the polling information that the player receives at that moment is recorded, as well as the global voting for the whole population. So we have like one time series for the whole population, one time series for each individual for the voting decision, and one time series for each individual for the voting they see throughout the game. And then once the game ends, the players were asked to do a post-game survey, including all demographic information and political affiliation and some open-ended questions. And they also did a dictator game, more kind of for exploratory reasons. So this is an overall view of our experimental setup. So we had groups of participants coming from Amazon Mechanical Turk, and then once they recruited, they were redirected to breadboard, where they were able to interact on the network structure. And then we collected data, we changed experimental parameters, run another set of experiments, and then also pay the participants according to their payoff throughout the game, plus some show-off fee for participating in the game. Sure.
So what is the polling?
I'm sorry.
Yeah, this is probably because you have PowerPoint and you put it on Keynote.
Yeah. So I think. This one?
Yeah, so what is the local polling information?
So that local polling information is the aggregated votes, aggregated intended votes of my neighbors in the social network. Yeah. Sure.
How are they positioned in the network? Are they randomly?
I'm going to talk about that, particularly how so their position on the network is random. But the structure of the network, I'm going to talk about it in a few slides. So here's the setup here's the interface of our game. So it's kind of like embedded within Amazon Mechanical Turk. So players then need to go to another platform to do the game. On the left-hand side, you can see the aggregated vote or the local polling information from the players or they are connected to. So how many of my friends in the social network are voting for purple versus yellow? And what is the supermajority threshold for this specific game? And then there we have like a timers, like 4 minutes, timers running out. And then which team I am assigned to, and what is my current vote. And then we also give them a kind of like dynamic description, whether like, okay, for example, in this case, nobody's winning the game based on the polling information, but yellow is ahead. And also remind them that the vote they're seeing is not represented, doesn't represent the whole population, it's just portion of the population. So the ultimate outcome of the game can be different from what they see in their polling information. So another note on using this kind of methods and running experiment on networks is that these kind of experiments can be very expensive because you have groups of people and then you are measuring the group level outcome and you want to like for statistical reasons you want to like run a large number of these experiments. So it might not be very optimal and not very cost effective that you want to like run a large number of them and find a set of parameters that you want to like do the optimization or you are interested to study. So the systematic framework that we developed for this project was one attempt to address this issue for like designing experiment on network in a more efficient way. So the way that we did it, we started with a computational model. In our case, it was like a voting coordination game, which we simulated for our case. We made some prediction what will happen if you run the experiments. And then did pre-registration for based on our prediction, and we designed a set of experiments to test our prediction. And then we run this experiment, collect the data, analyze the data, check the reproducibility, and then fit the data again into the model and see A, if the assumptions in our model make sense in real world with actual human being, B, to fit the parameter and tune the parameters of our model. Once the model is updated, I can use the model again to make prediction about the real world experiment as well as find the right set of parameters or parameter space for my experimental design. It also helps me with the power calculation, so I know that how many replicates do I need to run for the experiments. So just give you an idea about problems that we had running this model was we started with a model for the voting coordination game where the assumption was that we need time series for the model, and then we need data to fit into our time series to make prediction. The first iteration of this model, we find that people do not change their votes over the course of the game that much. So it's more kind of like people are more kind of few times they change their decision over the course of the game, and it's not enough information to fit our model. So we went to our model and we updated the model so that we can account for the for the data we can collect from the experiment. So these are the 4 different waves of running these experiments. So the first step, we designed an experiment where we had a single human being and a group of bots, but the human being didn't have any idea about that the other players are bots. So it gave us this freedom to manipulate the outcome both of the voting, like the local polling they can see over the course of the game, as well as the ultimate outcome. So we ran this for different conditions of the outcome of the game. So different conditions for the polling as well as different conditions for the ultimate outcome. Once we have that data, we fit it into the model again, and we run another set of experiments where we look at the different incentives. Here's by incentive, I mean the ratio of the winning team, the incentive of the winning team versus the losing team. So we did that and fit the data into model, and then we went for another set of experiments where we look at the effect of bots. So look at whether the case we don't have bots, whether we have like number of bots, half of the human and equal number to a human, and two conditions for where the players know that there are bots in the game and where they do not know that there are bots in the game. Once we have all this information and fit them into the model, we had a good idea about what would be the right parameter space for our experiment. We went for our ultimate goal, which was looking at the different network structure and the effects of bot location on the network. For which we ran another set of experiments, was like 20 replicates for if different conditions of the bots, which I'm going to talk a little bit more in the details in the coming slide. Around like 2,500 players total. So that was like basically the results of each phase was used to update an outcome model. Then an outcome model prediction was used to design the next set of experiments. Cool. So let's get back to our original question. So what are the features of the network that play a role in the ultimate outcome of this kind of ecosystems and like collective decision making? So players can see the votes of only of their neighbors. That is, there is a directed influence network that defines how I can see other players' intention to vote or like preferred party. So the first question that comes in mind is that what features of this network play a role in putting one party in a better position than the other party? So what do you think, guys, would be like helping a party? What feature of this network will be helpful for a party to win the election? That could be one. So like if there are like higher degree distribution, the one party had like larger degree per nodes. So we can think about a couple of different features. One is the number of nodes, basically, which is the simplest one. So if there are like more actors from one party, they might have higher influence over the opposing party. Another one is the amount of is like the number of edges, which or degree, which Iman said. We can also think about maybe other features like clustering coefficient or like modularity or degree distribution can play a role in putting one party in a better position compared to the other party. Sure. So modularity means like when you have nodes clustered together, there are like more connections between a group of nodes, and there are less number of connections between the two clusters. So more kind of like a high community structure within the network. So that's correct, and then they can play a role in putting one party in a better position compared to the other party. But another question is that if all of these things are equal, are there other features in the network that can help one party wins the election? So that is, if they have the same size, every node has the same influence, what else can help one party to take advantage in the election? But still think about it with like players are randomly assigned to different nodes in the network. I mean, there aren't like heterogeneity among the players in that sense.
So you're saying that players are randomly assigned to the nodes, or so there could be variation in degree each party?
So think about the network structure with the degree of all the nodes is the same. So basically, we don't have like variation in the degree distribution at all. And So the influence is the same for like each node.
So, I mean, randomly, you could have one party receive, well, no, that's what we all know that. So I'm thinking of a case like, for example, that you could have one node of a specific party surrounded by nodes of the other party, and then he will change, and then when he changes, you can create a cascade.
Yeah. So that's the case which we refer to gerrymandering. So think about these two cases. On the left-hand side, we have a gerrymandered network where there are equal number of players from each party in one player influence network. So if I'm purple, I'm including myself, there are two other purple, and there are three yellow in my influence network. We refer to as ungerrymandered network. Whereas on the right-hand side, everything equal, but we see that if you look at this a little bit deeply, you see in this one is like kind of like gerrymander for the purple team, where you have group of yellow kind of like clustered together, so they wouldn't change their votes. Whereas for these poor players, they're kind of like surrounded by purple players, so they're more likely to vote purple because they don't want to like get deadline. So that's something that we refer to as information gerrymandering within this setup. So let me stop this. Oh, can I stop this? So for example, look at the way that we generate this kind of network to keep everything else equal is that we create these clusters of nodes. If I can play this somehow. Oh. Yeah. So the way that we do it, if you look at here, we create clusters of players. So in this case, yellow is gerrymandered for yellow. So we create clusters of nodes. These are all purple. These are yellow, yellow, and then we have like a couple of purples which are surrounded by yellow teams. And then keeping everything equal, I mean the colors within the influence network, we rewire the network hundreds of thousand times. So we end up with a completely random network where the edges for each network is the same across the whole network. But the influence network of the nodes have the feature that we can see on the right-hand side. So there's nothing specific about the structure of the connection between the network, only the way that the nodes are embedded within the network, or like the kind of assortment within this network. Oh my God. Okay. I mean, I tried to explain it from this broken formula here for Mac versus PC thing.
Yeah, it's like PowerPoint doesn't go well with.
Yeah. But anyway, I think it should be clear. So the question here is that how we can quantify this effect of information gerrymandering, or something that we also refer to as assortment. So one way of doing that could be the way that we structure the network would provide us with some intuition for coming up with a metric for each node. That is, for each node, I can say the proportion of the players in my influence network that are from the same party that I am. So if there are more, if I'm purple and there are more purple in my team, there is an assortment in favor of my team. So here delta is positive. If the delta is more than 1/2, it's in favor of my team. So it's like more than half of the players are supporting my party, my influence network. Whereas when it's not the case, there's a negative assortment, which is meaning that I'm embedded in a influence network, which is kind of gerrymandered for the other party. And then by that measure, we can easily do the average for the whole network structure, saying that whether this network is gerrymandered or like is in favor of one party versus the other party. So this more kind of like a variation of the influence network, but we can think also about where we have the case where the voting is kind of a structure, where the assortment is kind of skewed toward one party versus the other party, if that makes sense. So that is, if there is only like some variations, but if the variation is symmetrical between the two parties, or the variation is in favor of one party versus the other one. I'm going to give you an example about this. So let's keep that in mind and then go back to the results that we obtained from our experimental setup. So we ended up our mathematical model represent the strategy space of the players with the probability they vote for their own party, which is based on the vote they can see. Either they're going to vote for their own party or the other party based on whether their team is winning or not. We also observe a significant endgame effect. That is, in the first half of the, not first half, in the first like 200 seconds of the game, people completely decide differently from the last 40 seconds of the game. As in many cases, they were kind of like, I'm trying to vote for my own party, whatever. And then when they're getting close to the last few seconds of the game, they're going to say, I'm going to vote for whoever is winning because I want to get like 50 cents, which is better than nothing. So in our mathematical model, we basically represents each agent with a strategy vector of 6 elements like this. And then once we have the data for the null hypothesis, we could simulate for different influence network to see what would be the outcome of those different structure for the network. So just to make it a little bit more clear that what we studied in the last part. Sure.
What is the null model?
So, I mean, null, like the base model was the case where we have the balance assortment. So think about this network when I don't have any assortment and I don't have any information gap or like skewness. So each player, there are same number of players from each party in each influence network. And there isn't any bot in this network. So we ran a couple of replicates for this structure, and we ended up having this distribution for the vote share, for example, in this case for yellow team or like purple team, or one of the team basically. So we see it's kind of more, these are the supermajority threshold, and these the blue ones are the distribution coming out of the experiment, and the gray ones are the distribution coming out from the mathematical model. So we had that one, and then we look at different cases of information gerrymandering. So in the left-hand side, we have cases where all 24 players are human beings. And the right-hand side, we have cases where there are also bots in the game. And then like 18 players, human players, 6 bots. So this case is where there is assortment. There is also information gap. For if you look at it, it's more kind of in favor of yellow team. And then similar condition, but we also have bots. And then we have cases when we have symmetrical assortment, where we don't have information gap here. So that is, if you look at this, there are kind of variation in the influence networks, but this variation is the same for both parties. And then the same thing with bots. So if you look at the outcome of these setups, we see, comparing to our basic model, like a null model here, we have more skewed voting in the favor of the team where there is more gerrymandering going on for it. Same thing kind of skewed when we have bots. But when there is a case when there isn't any skewed voting, but there is assortment in the network, kind of like symmetric assortment, there is a higher chance of getting deadlock comparing to our baseline. So that is, information gerrymandering leads to biased outcomes, and assortment here, or like polarization, leads to more deadlock. And ultimately, zero-sum view players, or like zealots or the bots, can induce bias in these setups.
Okay,
Sure.
so in your study, bots do not change their.
So yeah, I mean, I should have said that. So we mainly put them like dumb bots, which are like vote just for the same team that they were assigned to. Which we ended up so when we infer the strategy of the players in the game, we also have like real zealots or real human being. So when we infer the strategies from the game, we have some players that vote on their team no matter what, no matter what. So even if they see that their team is losing, they change their strategies. They don't change their strategies. We have some players, another type of players, who are like change their vote immediately when they see the other team is ahead but is not winning. And then we have another type of players who just vote for the other party when they see they pass the supermajority threshold. And these kind of strategies different in the beginning of the game, the first 200 seconds, than the last 40 seconds. And so one of the understanding that we have is that people are more kind of looking for behavioral factors in the first 200 seconds and become super rational and selfish in the last 40 seconds, which in case they want to like just maximize their payoff. So that was mainly the case where we look at the experimental results, but we also look at the same features of the networks in real world. This is, for example, the case of bill co-sponsorship in House of Representatives in the US. So we look at the network of the co-sponsorship of the bills over the past few years, and we look at the assortment within this network and compare it with the actual polarization within this crowd. You can see once the assortment, in this case I think is Republican, that's going up, and it's kind of like catch up with the similar assortment like the Democrat one. You can see similar patterns emerging in the actual polarization. And we look at the similar pattern across a couple of other networks, and we can see not only in many real world networks there are kind of assortment going on, but there are also kind of skewness toward one party versus the other. And with that, I would like to conclude, and I'm happy to discuss any questions you might have. Sure.
I have a question. So, looks like in the game that you have, there's no cost really for players to change their opinion, to change their party, because what's really important for them is the payoff that they receive. But in real elections, almost everybody is a zealot. We have ideological beliefs, and even if Republicans are winning, I'm still gonna vote for a Democrat. So how do you connect these results? To
Yeah.
elections?
So in the beginning, I didn't talk about this, but we actually included another measure in our experiment, which was more kind of like they call it DIFI, like Dynamic Identity Diffusion Index, where we ask people whether they identify themselves with the color they assign before and after the game. Also look at how people's strategies different throughout the game based on the way they identify themselves with the game, with the color. That kind of captured the idea that you are mentioning. The other way of doing that would be like also assigning some cost to people if they change their mind, or like there isn't any stickiness of the voting party here. There could be some because if I vote for the other party, I'm losing the money. It's like kind of like capturing that, but not exactly. So you can also another version of this model can be you also assign some cost for like changing votes, like some monetary value for changing that, but it's not something that we have done. And at the end of the game is more kind of like a minimal paradigm thing that where you people like assign to different colors and like actual political identity. Sure.
How could you, do you have any real situation where you could map this payout structure in real life? I mean,
Yeah, I mean, one example I usually think about is like, think about like Sanders supporter and like Clinton supporter. I mean, if I'm a Sanders supporter, I would love to vote for my candidate will make it. But either way, if I see that he doesn't have that much chance, I will go and support Clinton, which is better than not than like the whole party doesn't win. Also, there are like cases for more kind of like political figure when they want to make decisions within their own parties. So like Republican, they want to like have make some decision collectively that's good for all the people, but there are kind of like polarization within the whole party itself. Sure.
Why did you decide to have supermajorities? Why not just about 50%?
So because you don't have deadline in that sense, and you have so much noise.
Yeah,
It's like
why do you need deadlocks in any oh, so I understand the noise that
yeah, I mean deadlock was like kind of like intrinsic to the model itself. We want to like have this dilemma whether you want to like avoid you want to like so the intrinsic characteristic of the model was like you want to come into some form of consensus whether it is in your own favor or the favor of the other party, but it's good for both of us rather than like not making a decision, not being able to come into a conclusion at all. So that like a deadlock thing is kind of like intrinsic to the model. And the way that we selected the supermajority threshold was through the calibration part. So we found we tried a couple of different supermajority thresholds and see which one of those make more sense for our analysis. So we tried like 60, 70, 80, and then see which one is better for the statistical test that we wanted to do. Sure.
So my background is not in network science, so I guess my question is, so what does something like this or this approach tell us that like a typical median voting theorem model, or something that's scaling methods or anything like that wouldn't tell us before?
So one key aspect of doing all this experiments stuff is adding some more realistic features to the mathematical model that we built before. So think about like as many so the UPenn people are biological mathematicians, and they're super good at like building a model, coming with a solution, like an analytical solution, and then look at the dynamics of these things. And they didn't see like experimental data before this project. It was interesting to see that they said, okay, this is a well-behaved model. but it doesn't work with real world. This is not the way that actual people make decisions. So that's one key aspect of running these kind of experiments. And another one is also looking at all these behavioral factors of the model. So if you want to, like, for example, we didn't know before, bless you, before running this experiment that like people, we weren't expecting this kind of end game effect thing before like doing the actual experiments. So, and it's the cool thing about, so if I usually like think about two end of the extreme, where on one hand you have this mathematical model, on the other hand you have the empirical data. And many people find like assumptions from the empirical data and then start building models. But the problem is that the mathematical models they build cannot be applied directly to the empirical model. You cannot find an exact case in real world where you can look at this mathematical model like the Boolean coordination. But the cool thing about like running experiments on networks is that it's the exact paradigm. You know, just the same game that you're analyzing in your mathematical model, the same game people are playing that. Being played by people on empirical data.
Well, thank you so much for your time.
Thank you.
Let's thank our speaker one more time. So we have Tiffany sitting up in the back, so we'll all be able to meet shortly.